general a little bit about the next couple of weeks. 2 weeks from today is a teacher work day, so that means we have this week and next week to be able to finish up the third quarter. So this week you had finished up, or you had completed in its entirety all 4 parts of the investigative task. The investigative task in all 4 parts was 80 points. What do you guys have due on Friday? The inference portfolio, that's 100 points. 10 individual sheets of paper must be turned in with that, okay? Those templates are online, so make sure that you are aware of where they are. That's a major grade. Also on Friday, so you're going to have 3 textbook problems and some just checking problems to do for homework tonight. So it won't be a lot of homework. On Wednesday, the only homework you're going to have is the portfolio to finish up any loose pieces and to study for a quiz. You will have a quiz on Friday on what we're about to do, okay? What we do today and what we do Wednesday, all on chi-squared. So kind of keep that in the back of your mind. So that's what's happening this week. Next week, you will have a test on inference that will cover all of it, okay? And that will be our last grade for the quarter 3. Yes, ma'am. No, what's due for the portfolio is already done. You do not need to do chi-squared for the portfolio. Just 1 through 10 only, okay? All right, any other questions? All right, let's go ahead and get started then. We have so far already talked about the normal distribution, and we know what it looks like. We've already talked about the t distribution. And today, and both of which are unimodal and symmetric, today we're going to talk about something called the chi-squared distribution, and it is pronounced chi, not chi, okay, and it is like an X, looks like an X, but it's got a kind of a squirrely or a swirly curved X, almost like a script X, if you would. But the shape of a chi-squared distribution is not unimodal and symmetric. It is definitely skewed right, okay? So interesting that they're different shapes for sure. They all deal with different types of data as well. If you remember, back early on in inference, I had you ask yourself a question. Are we dealing with proportions or are we dealing with means? So when we talk about normal, is that a proportions question or is that a means question? Normal deals with proportions, okay? One proportion z-test. Z-scores are using the normal distribution, okay? So normal distributions deal with proportions. How about t-distributions? What kind of data are we looking at, or what kind of statistics are we looking at? Proportions or means, okay? So we're dealing with means here. Both of these things are quantitative data. Would you agree? Both of these are quantitative, measurable. When we get to chi-squared, we're now dealing with qualitative data, categorical data, qualitative. Okay? We're talking about counts as opposed to means or proportions. Okay? We have this many people that have blue eyes, and this many people that have brown eyes, and this many people that have green eyes. Okay? We're looking at categorical data and actual counts of that, of numbers of things in those data. When we looked at the normal distribution and we looked at proportions, how many different types of tests were there? We had one sample, which was the one proportion z-test, and then we had the 2 proportion z-test, right? So we had 2 different types. How about with t-distributions? So we had 1 proportion z-test, and we had 2 proportion z-test. How about t-distributions? What kind of tests did we use with that? 2 sample t-test. What else did we have? Matched pairs. And then what was the 1 sample called? Let's just call it a regular old t-test. 1 sample t-test. Okay. With chi-squared, we actually have 3 different chi-squareds. And we're going to talk about 2 of those today, but there are 3. One is the chi-squared goodness of fit test. We're going to talk about what differentiates those. Sometimes we call that GOF, goodness of fit. Number 2 would be homogeneity. And the last one is independence. They are all chi-squared tests. They all deal with qualitative data, categorical data, and their counts. They just have different purposes. Sometimes, like goodness of fit, for example, deals with 1 sample. Homogeneity deals with 2. So it's kind of like your 1 sample versus your 2 sample situation. But independence is a little bit different. It talks about whether or not variables are independent of each other. Is hair color independent of eye color? We did that from a probability standpoint months ago. We're going to do it from a testing standpoint next on Wednesday. Problem number 1, or a goodness of fit, is what we're going to do, spend most of our time today. These 2 will spend most of our time on Wednesday. Okay, just kind of FYI. Now, just like with the other 2 distributions that we've used before, when you're doing a test, you have 4 steps. And those 4 steps are the same 4 steps all the time. What's step 1? No, what's step 1? Hypotheses, right? Null and alternative hypotheses. What's step 2? The conditions and naming one of those tests. What about step 3? The test statistic. Now, and the p-value. Now, with the normal, remember back when we did a test statistic, there was a z-score, and it looked kind of like that. Would you agree? Now, maybe you were subtracting the 2 means, or maybe you were, the standard deviation, you had to divide by the square root of the sample size, or maybe it was the square root of PQ over N. We're not sure, but the standard deviation has many forms, right, depending on the kind of sample you're looking at, but that's generally the test statistic. Same thing for t, really, isn't it? Same idea. With the chi-squared, it's a little bit different, okay? And there actually is a formula, and it's on your formula sheet. It is in the second, or the last column at the bottom, and we're talking, you can look at it if you have your formula sheet, it's there. But just so you know, you don't have to memorize it. But I have the formula here in red, okay? So we're going to look at that formula in a couple of minutes, but it has its own test statistic. Please do not get confused with the squared with chi-squared. Do not get confused with this. That does not mean you're squaring anything. It doesn't mean, it's just called chi-squared, okay? It has nothing to do, it's not a mathematical squared. All right, so we're going to come back to that. Now, when you're doing a chi-squared goodness of fit test, there's 2 things that could possibly happen. And we're going to look at both situations today. You can assume that the values are either equally distributed, and we're going to do that one during the second example, or it's going to provide a historical population. And that's what we're going to look at first. So you don't have to write this down or anything. I'm just going to explain that there's 2 different possibilities with this particular test. The conditions are awesome because they're easy, okay? There's only 2 of them. 1, you want your sample to be a random sample, or at least if it's not random, what should it be? Representative, so it's one or the other. And then the second, we'll have to explain a little bit more in a minute, but we have to look at the expected counts, and they need to be at least 5. And that's it. Those are the only conditions for any chi-square test that you have to check. Bonus, okay? That's awesome. Important thing is that the data must be counts, okay? You have to have the number of people in each category, or the number of things in each category. The data is counts, not percentages, okay? Not proportions. In a goodness of fit test, we have 1 sample. That's very important. If you have more than 1 sample, you cannot use this test. So one sample test. In that sample, you're going to be taking that data, or it should be given to you, divided into categories. And it's important to know what the categories are, because that's how you find your degree of freedom. Because there's going to be a degree of freedom like there was with a T. Okay? So one sample, we're looking at categorical counts. We can do that. We can recognize that data, I hope. Here's the formula for a chi-squared test statistic. And we are going to do the first one by hand. So you definitely need a calculator. I'm going to show you what observed means, what expected means. What does that weird-looking E thing mean? Sum, not average, it's actually the sum. It's when you add them up, okay? So it's the sum. So I'm going to show you how to compute that using the sum. Notice here you see that degree of freedom is n minus 1 like it normally is, but n's not the sample size this time. In a chi-squared, n doesn't represent the sample size, n represents the number of categories. So it's important to know how many categories there are, and you just subtract 1 to get your degree of freedom. We already talked about what the conditions were. Random and counts are less than, expected counts are less than 5. Or more than 5, sorry, more than 5. And again, this formula is on your formula sheet. Jenny has hers here to show you right here. Okay, bottom right. Nothing to memorize. Woo-hoo. All right, do not write all this down. So let me just kind of go through what's important. In any chi-squared test, whether it's goodness of fit, homogeneity, or independence, the hypotheses are written the same way. It's kind of nice. There is no direction, one-tailed, two-tailed, greater than, less than, with a chi-squared. It's not unimodal and symmetric. It's just skewed. So we're only looking at greater than scenarios. Only. Okay? So you don't even have to enter that information. It doesn't even come into play in terms of, remember on the test on the calculator it asked you if it was greater than or less than or not equal to? Doesn't even come up. When you write the hypotheses, and this might be something that you want to write down, a null hypothesis is really always going to be the sample distribution is not different. Okay? It's not different from what? Either the historical one, the one that was provided to us for comparison, or it's not different from each other. It's one of those two scenarios. And again, we'll look at both of those today. The alternative is just that the sample is different, either from each other or from the historical perspective. Okay? So you just have to put this and then the context, and it's really the same every time. It's kind of nice. When we get to homogeneity and when we get to independence, we're just going to change a word here or there, but it's basically the same thing. Either it doesn't differ or it does. Okay? Nothing too exciting yet. Don't write anything else down, just kind of listen. All right? I've already really said this. The null hypothesis, or the alternative hypothesis doesn't give us a direction at all. So we don't have to worry about that, whether it's greater than or less than. We're just concerned that it's different, that it's changed. Okay, and that's really what that's saying there. Good enough. All right, so let's just, I think the best thing to do is to jump in. So we're going to look at this example. Okay, this is one of two chi-squared examples that we're going to do in class today. And I want to do it from beginning to end with all 4 steps. So I want you to read this. You can copy it down, it's fine. I'll pause the recording. While you're copying it down, I want you to identify why it's a chi-squared test. What in the problem tells me chi-squared? Okay? Why is this chi-squared? What kind of data is it? Don't worry about the historical part yet. That's part, we're going to get to that. There is one, you're right. But why is it chi-squared? Qualitative data. What are the categories? Grades. Okay? The grades are is the variable of interest. Okay? How many categories do we have? There's 5 categories, A, B, C, D, and F. So that tells me, what's my degree of freedom? Five minus 1. So my degree of freedom in this case is going to be 4. Okay? It is qualitative. We do have counts, right? What the counts? I see percentages up there too. But I'm concerned about the counts right now. We'll get to the percentages because they do mean something. These are what? Remember in the formula for chi-squared we saw an observed and an expected. Which ones are these? These are the observed. This is what happened in her class, right? These are the observed values. We're going to find the expected in just a minute. Okay, you have to find those. They aren't just given to you. So we have the observed. What are the percentages? And that's what Cameron was suggesting. What's the percentages? What did you say a second ago? It's the historical, it's what we're going to compare it to, okay? So it is, it's the historical distribution that we're going to take our class and compare it to. So that's okay to be percentages. What's not okay to be percentages would be these numbers with the letters, okay? Those can't be. Those are considered counts. So I know it's going to be chi-squared. How many variables are there? 1. How many samples are there? 1. That tells me it's goodness of fit. Okay? So when I say expected, I mean we're going to literally find how many A, B, C, D's, and F's we expect to find, or we expected to find in her particular class. Well, you know what actually happened? Those are the observed values. But how many did we expect to happen? How can I use those percentages, 15%, 30%, etc., to come up with what should have happened or what we expected to happen? Byron? Exactly. So we're going to take all of these numbers. We're going to take the 89, the 121, all these numbers and add them up. Find the total. How many total kids did she teach this year? Go ahead and add them up. Tell me what you get. And this number will be 15% of that. Did you get 325? Okay. So in other words, the number of A's we expected to happen would be 0.15 times 325, or 15% of 325. Now, what number do you get there? Like 90 something? Oh, 40, sorry, 48.75? Okay. So 48.75. Now before, when we did this in our calculator, didn't we have to round that? When we did proportions, it didn't like when we put decimals in, did it? It's okay here. So these are just expected counts. They're not what actually happened. It's not part of the sample. The sample numbers cannot be decimals because they're counts. The expected ones can be. It's not a big deal. Okay? So do me a favor and go ahead and populate the rest of this. This is going to be, the B's would be 30%. So we're going to do 0.3 times 325. And we'll go ahead and just use all of the percentages that you see across here to populate the expected value table. So it'll take you a second to do that. Did you get those numbers? Just double check. So we found our expected values. What am I looking for with my expected counts or my expected tables? It has to do with remember the conditions? What do they have to be bigger than? 5. That's all you care about. Are they all, each one of them is bigger than 5, is it? Basically, that just means your sample size is large enough, okay? You need a large enough sample, and you did, so you're good. All right? Perfect. So my expected counts are all bigger than 5. So when we do our full hypothesis test, we've met that condition. So let's start it. Step 1. What is the first step in a hypothesis test? Not the conditions. That's step 2. The hypotheses themselves. Good. in this context, what would it be? We're not going to use the word chi-squared, actually. What did I say before? The distribution is the same. It doesn't differ. Is the null hypothesis. And then the alternative would be is that it is different. Okay? Different from what in this case? The percentages, right? So we're going to say in context that our sample, the biology professor's sample, is not different from the historical distribution, the percentages. Okay? So that's the null hypothesis. So the bio professor's grades are not different from the historical distribution. Okay? What would the alternative be? So Maddie, you should be writing this down, babe. I'm sorry? They are different. That's all you have to say. Okay? The bio professor's grades are different. Okay? We're still going to find a p-value. We're still going to find a test statistic. We're going to do all the same steps. We're just not there yet. Take a second for you guys to write this down, get caught up. We want to be thinking about step 2. What would you say, Jenna? How should I start with that? What's step 2? Conditions. Before I get to the conditions, I should probably say what? The name of it. What kind of test is this? You want to say chi-squared also, okay? Don't just say goodness of fit. It's a chi-squared goodness of fit test, and that's what we should say. And I am perfectly okay if you just simply say that, okay? You don't have to write out CHI. You can just say chi-squared GOF. Perfect. All right, now we'll jump to the conditions. How many are there? 2. Yay. What's the first one? Well, in this case, it's going to have to be that, Angelica, isn't it? It's not a random sample. Okay, it does not say that she did a random sample. These are kids in her class. What we have to assume, since it's not random, is that it's representative of her bio classes. Okay? And so that's what we'll have to say. So we're going to assume that the sample is representative of her bio classes. All right? How about condition 2? What's greater than 5? You have to be very specific. What counts? Not sample counts. It's the expected counts. And we're going to be specific that you know that. It is the ones I wrote in red and blue over here. Okay, the expected counts, so this is what you would say. All expected counts are greater than 5. Okay? And you've written them there. You've proved it to me. I can see that because you've found them. You calculated what the expected counts were. So, and we can see that. Okay? Before we get to the math, because, you know, there's not enough math in statistics, but there is in this particular calculation. It's like this and standard deviation. I feel like they're the only 2 math things we do all year. Okay? We're about to do some math. Tell me, are there any questions so far before we get into the test statistic part? All right, so step 3 then is our chi-squared test statistic. And we have a formula for it. Just to remind you, it is the sum, let me write the word sum, or the symbol for sum. It is the sum of the observed minus the expected squared divided by the expected. Okay? So we are literally going to look up here at what I've highlighted in yellow. Let's start with the A's. Then we'll move to the B's, then we'll move to the C's. But right now, we're just looking at A's. What's the observed A count? 89. What's the expected A count? 48.75. That's kind of big difference, don't you think? They're kind of far apart. That leads me to believe that, maybe they are different, right? Maybe our p-value will prove that. Let's see. So 89 and 48.75. So here's what you're going to do. You're going to say 89 minus 48.75 quantity squared divided by 48.75. You're just taking those two values, the observed and the expected, and plug them into my formula. To that, I'm going to add. I'm sorry, go ahead, sweetheart. Yeah, where does the sum come? Now we're going to add. Now we're going to do the same thing for the next category. Okay? What happens with the B's? So in the next category, we have 121 and 97.5. Do you understand where those numbers are coming from? Okay, so that's what we're going to plug in. So we're going to say 121 minus 97.5 quantity squared all over 97.5 plus. Then we'll do the same thing for the C's, and the same thing for the D's, and the same thing for the F's. Okay, so I'm going to pause the recording. I want you to go ahead and just write down, using the numbers, the rest of the formula. On your quiz on Friday, I am going to be expecting to see this written out. Okay? Assuming that the number of categories is small. We're going to do one in a minute where there's 12 categories. I wouldn't want you to do that by hand with 12, okay? But with 5, it's not that many. I want you to tell me what each of these contributions are. So find this one. Tell me what number it is. So you're literally going to find each of the contributions individually, and then give me what chi-squared is, okay? So you're going to find 5 numbers and sum them all together. So the key is not to round very much, but I can show you. So this particular contribution matches up with this number. This particular should not have erased. This particular contribution matches up to this, and so forth and so on. Okay, you get the idea. So I'm looking for the work, that you know how to use the formula, that you've actually simplified it, and then you found the sum. Okay? I'm also going to show you how to do it on the calculator in just a minute. We'll get there. Okay? In step 3, what else do we need to find besides the test statistic? The p-value. Okay? And so we're going to draw it just like we did before, but this time we know that it's a skewed right picture. We're going to put 62.538 on it. And we are always looking for a greater than or a right, that particular probability. Okay? Now, when we did normal, we used normal CDF. When we did t-distributions, we did t-CDF. Guess what we're going to use this time? Chi-squared CDF, and there is one. Okay? So the p-value is found using it. So chi-squared CDF. If you plug it into your calculator, it's going to, and by the way, I believe it is option 8. Okay? So chi-squared CDF on option 8 is going to ask you a series of questions. It's going to ask you for a lower bound, an upper bound, and a degree of freedom. According to my shaded area, what's the lower bound? Of the shaded region, it's just 62.538, right? So 62.538. Of my shaded region, what's the upper bound? Some big old number off to the right. We're going to call it E99, which just means 1 times 10 to the 99th power. And then what was my degree of freedom? 4. The number of categories minus 1. So go ahead and type that in. Tell me what kind of p-value we get. Very small. How many zeros does it have? 12. Okay, it's really small. Was it like, the one thing I don't want you to tell me it is it's not 8.5. Would you agree? It's 8.49 times 10 to the negative 13th. You can say that. Would you agree with that? Make sure you realize that's a really small number. So I'm going to say, I'm sorry, negative 13. There you go. It's approximately 0. Would you agree with that? It's that small. Okay. Found a test statistic, found a really small p-value. What does a small p-value mean again? Reject that thing. Okay? So step 4. We're still going to have linkage. We're still going to be comparing our p-value to our alpha, which we're going to assume to be 0.05. Make sure you know which direction to put the inequality. Remember, it eats the bigger number. We are going to reject our null. And then what am I going to say in context? We have evidence to suggest, I love that you're starting it that way, suggest what? The grades are different from her historically, the grades are different this year. Okay, we have evidence to suggest that her grade distribution is different than it has been in years past. That's probably how I'll say it. So what's different about the chi-squared goodness of fit test and any other hypothesis tests that we've done to date? We've done at least 5. The conditions are different. What else? The what? The formula for what? The test statistic is different. What else? The degree of freedom is different. The shape's different. What about the hypotheses? There's really no direction. We don't have to worry about our alternative hypothesis. It's never going to be wrong, right? It's just going to be, it's either different or it's not different, okay? So you just have to remember which one goes where. We don't have to worry about a greater than, a less than, or a not equal to like we do with the others. But the steps are still the same, right? I mean, nothing's, I mean, there's been some minor things that have changed, formulas and conditions and that, but the process is still there. Question? Yes. For a chi-square, you'll always shade to the right. And the reason for that is because that's where the tail is, right? Since there's not 2 tails, we have most of the data, and so we're always going to shade in that direction. Good question. Okay? There is no confidence interval with chi-squared. Okay, so that's good news. I like that. Don't you like that? Okay. We only have one more confidence interval to go, and it has to do with what's called a Lin-Reg t-test, and we'll do that next week. Don't worry about that today. The end is near. We're close. Do you want me to show you how to do it on the calculator? Please, Mrs. Natter. Okay, so let's do it. Maybe. All right. What I'd like for you guys to do is to get your calculators out and find where chi-squared goodness of fit test is. There are actually 2 chi-squared distributions. If you go to distribution, you scroll down, you'll see option 7 is, not the right thing, sorry, it's tests, stat tests, not option 7. Keep scrolling. There you go. Option C is a chi-squared test. That's not the one we use here. We use the goodness of fit test, which is option D. The GOF, goodness of fit test, is a new option, okay, which means if you have an older calculator at home, it might not be on there. Just keep that in the back of your mind, okay? It's new within the last, I think, 5 years or so. Like, I have an old graphing calculator that my 14-year-old uses. Like, I think it's a TI-83 or something. Like, it's mama can't sport for a new one, but it still works, but he doesn't have to do goodness of fit test, okay? So just be aware of that. But we're going to use goodness of fit test. If you hit it, look what it asks us. Can you put your observed data in list 1 and your expected data in list 2? So let's do that, and then we'll come back to this, okay? Where are my lists again? Stat and edit. So you want to make sure that we clear those out. Maybe. If my smartboard is working. Clear them out and go ahead and enter those values in. And again, observed goes in list 1, and expected, the ones we calculated, go in list 2. So I'm going to pause the recording and enter that information. So I've got the data listed in list 1 and list 2. We're going to go back to our tests. We're going to choose option D again, which is our goodness of fit test. We have to change our degree of freedom, though, to what? 4, because it's the number of categories minus 1, and we'll go ahead and calculate it. Notice the chi-squared is the first number. That's your test statistic. But I want you to really pay attention to what I'm about to show you. Okay, so I want to see everyone's eyes up here. I want you to compare these contributions to what you see on the calculator. Do you notice where it's, well, hang on. Do you notice where on the calculator it says CNTRB? That means contribution, okay? So what we can do, all right, this thing is being grumpy. Just stay right there. If we arrow to the right, notice the first number is 33.2305. If I arrow to the right, it's scrolling, there's a space, and then the next one comes up at 5.6641. If I keep scrolling, what do you think is going to come up next? 20.8. Let's see if it does. Sure enough. All of the individual contributions to your chi-squared test statistic are on the calculator. So you can check them. Okay? It's kind of nice. So even though I'm asking you for all of this work, the calculator gives it to you too. You're welcome. Okay? Did we get the same p-value? The p-value we found using chi-squared CDF was close to 0. And guess what? The p-value is the same thing here as well. Exactly, actually, isn't it? Exactly the same. Okay. So we can check it. It's pretty simple. Any questions? Yes, sir. For the quiz on Friday, yes. Okay. Will they expect that on the AP exam? Okay. What they might do is give you the chi-squared value, give you one of the contributions, and ask you to find an expected value or something like that, and have you work the formula backwards. I've seen that before. Okay. I'd like to do one more example of goodness of fit before we jump into the second one, which is homogeneity. And it's going to be from the textbook. And it's the very first example that they give you. So I'm going to give you the framework and then give you the data. This is a chart that they gave you, or that I read about, that deals with zodiac signs and number of CEOs in Fortune 500 companies and what their signs are. Everyone know what their like astrological zodiac sign is? Depends on when you were born, right? Is anybody balanced like I am? Anyone a Libra? Libras, we're balanced. Oh, Hey, we're balanced. We're not crazy. Okay? We're not going to go off the deep end on one end or the other. We're nice and balanced. My kids might disagree with you on that, but anyway. All right, so I'm going to pause the recording. This is going to be the number of people, and then whatever their sign happens to be. I'll say their zodiac sign. And basically, it was a study of Fortune 500 companies that said, do you think that maybe certain astrological signs give birth to more CEOs than others? Okay, so there was actually a study done. And so we'll see if that's true. So let me give you the data. So there's your data. And this is actually a true story. Okay, I believe the name of the magazine that did this was Fortune. Okay, Fortune magazine, which is an existing magazine that talks about Fortune 500 companies. The top 500 producing companies, like money-wise, like gross product. I'm not sure if that's true. That sounds good though, doesn't it? I really don't know. That's a good question for your personal finance teacher, your business teacher. Come back with the answer though. Sweet. All right. So I have my data. First of all, someone tell me why I can use a chi-square goodness of fit test here. What kind of data do I have? What do I have? I have qualitative or categorical data. What's the variable? The zodiac sign, right? Astrological sign. How many samples do I have? One. It's the CEOs, one sample. How many different categories do I have? 12. One variable with 12 categories, okay, and one sample. So it is a chi-squared goodness of fit test. What's different about this question is that I don't have a historical thing to compare it to, do I? Like I did with the grade distributions. Historically, the grades broke down like this. I don't have that here. So what was the other scenario again? Remember I told you at the very, very beginning of class. I said that they're either, I can compare it to a historical or that they are equally distributed. So in other words, in this case, are they different from each other? So how would I calculate these are obviously the observed, right? This is our sample. These are the observed values. How do I find the expected? What would I expect to happen if they weren't different from each other? They'd all be the same number. What number would it be? The total number of people that are the CEOs, so add them up. I think I can just tell you. I want to say it is 256, okay? So it's the total number of CEOs divided by the number of categories I have, which in this case is 12. So what is 256 divided by 12? 21.3 repeating. So don't round, okay? So I want you to go ahead and perform. You don't have to write it all out in steps 1 through 4 in this case. You can use your calculator. But I want you to tell me what the chi-squared value is, what the contributions are, what the p-value is, and give me a result. Are they different? Is there one sign that maybe sticks out greater than the others? Do you think that you're more likely to be a CEO if you're a Pisces? Because there's 29 of those suckers, right? I don't know. You tell me. So I'm going to pause the recording. I want you to tell me what you think. When I'm plugging this into my calculator, we know what to plug in for L1. It's what's given to us here. What goes in L2? Oh, sorry. I'm plugging into the wrong thing. What goes into L2? The what? The expected, but every time, right? So you're going to put 21.3 repeating 12 times. It's the same for each one. So we've got our data entered. Where do I go from here? If I want to find the test statistic and the p-value, chi-squared. And I could do it all by hand. I happen to think 12 different contributions is too much to do using the formula. I would not do that to you. Okay, so on the quiz, if you're asked to do it by hand, they'll have 5 or fewer contributions, okay? So I think this is one I would just, okay to do it by the calculator. So we're going to scroll down to goodness of fit test. We've entered our data in list 1, list 2, but the degree of freedom is not 4. It's 11. Good. And we'll go ahead and calculate that bad boy. Is that weird? What does it tell us? Am I going to reject the null or not reject the null? I'm going to fail to reject the null. That p-value almost looks like I did something wrong. Wouldn't you agree? When you had a unimodal and symmetric distribution like the t-distribution or normal, when we had a p-value like that, that usually means we did our direction wrong. Remember that? I said that's kind of an unusual thing. When you have a chi-squared test, because there's only one tail, if you have a very small chi-squared value like you do here, 5 is pretty small. What was chi-squared before? In another example, like 62 something, wasn't it? So when I have a very small chi-squared, remember what the shape looks like. The shape of the distribution looks like this. Small chi-squared means I'm like over here, which kind of makes sense that I'm at 90-something%, doesn't it? So it's not unusual. Why do you think it's so high? Yeah, that just means there's no influence on zodiac signs. They're not different, right, from each other. And it kind of makes sense if you look at it. There's really not 1 or 2 or 3 that just really stand out. They're all in their 20s or thereabout. Wouldn't you agree? So nothing's really unusual. April, you got to lift your head up, darling. Okay? All right, so what I'd like to do is talk about homogeneity. I'm not going to do a full example, but I want to talk about why it's different, okay? So goodness of fit, how many samples did you have? 1. Homogeneity, you have 2, okay? So you're going to have in homogeneity 2 samples, 2 or more, by the way. It could be 2, it could be 3, it could be 4. And they have to be independent of each other, okay? So 2 or more independent samples. Often, and there's only one variable, okay? It is categorical still. You could still have zodiac signs, but maybe we're talking about CEOs, and maybe my other sample is people that are teachers, okay? And we look at those 2 samples and say, is one more influential than the other? I don't know, okay? So that would be a homogeneity situation. Oftentimes we look at years. If it represents different years, that's going to automatically be homogeneity, because you know that it's one thing connected are 2 different samples. Homogeneity. Another example of what could be homogeneity is an experiment, and you have different treatment groups. How do the treatment groups differ from one another? That could be homogeneity. The key is to look at the scenario, look at the context, and see, are there 2 independent samples? Is there one variable that I'm measuring? Is it qualitative? And go from there. The conditions are exactly the same as goodness of fit. The mechanics are exactly the same. The only thing that's different is your degree of freedom. The degree of freedom is this. The row, because it's going to be given to you as a matrix, kind of like a, it's going to be given to you, it looks like what kind of table is that? I think I say it up here. I'm losing my brain here today. Contingency table. So in a contingency table, you have rows and you have columns, right? So it's the number of rows minus 1 times the number of columns minus 1. So that's really kind of the only difference, besides we have 2 or more samples, okay? If you're given it as a matrix or as a contingency table, I'm not going to use list 1 and list 2. We're going to actually use matrices. So we're going to do that on Wednesday. Okay? So that's why you're not going to use the GOF test. You're going to use the other chi-squared test. But again, row minus 1, column minus 1. So we're going to look at a scenario. We're just going to set it up. We're not going to do it. I want you to tell me, 1, why it's homogeneity, chi-squared, and 2, what the degree of freedom is. And that's all we're going to do. Okay, and then we'll stop. Why is it chi-squared homogeneity? There is more than one sample. What are the samples? Yeah, you've got the treatment groups. Okay, so the 3 treatment groups are independent groups, right? You can't be in both. You can't be in a placebo and also take St. John's wort or whatever. They're different treatment groups. So I've got multiple here. I've got actually 3 treatment groups. That's okay. Is it categorical data? They're categories, wouldn't you agree? Okay, whatever they are. What is the category? What's being measured? What's the variable here? The diagnosis, whether they got depression or whether it returned or whether it didn't return. So the diagnosis is actually what you're measuring, okay, amongst those 3 treatment groups. So what's the degree of freedom? The number of rows minus 1 times the number of columns minus 1 is going to be 2 in this case, right? So that's something that you'll have to kind of calculate with a homogeneity scenario. All right, so let me go ahead. I'm going to assign homework. You have a couple, I've got some textbooks. You guys can start now because you have plenty of time to do that. You want you to read this chapter and be mindful that, I don't know why they do this, but they do all 3 chi-squareds in the same chapter. So we really only covered goodness of fit, which they barely touch on. We started talking about homogeneity and how it's different, but they also cover independence, which we'll do Wednesday. So what you're going to need to do is to read chapter 25 and do the just checking. Now, remember that you will, in fact, see, again, homogeneity and independence questions in there in the just checking. So just be prepared to read about those. But you're also going to do 3 problems that I've selected. If I can figure out where they are. I think it's 3, 4, and 14. These will all be goodness of fit questions. Okay, because those are ones we've done in detail in class. Okay, so 3, 4, and 14. So if you want to go ahead and get started, oh, and by the way, continue working on your portfolio if you haven't already. It is due Friday. I can't emphasize that enough, but I have several textbooks. You're just going to have to kind of get them underneath there.